Can you guys still see me? Oh, I'm back. Okay, I don't know what happened there. I'm sorry, guys. I don't know what happened. But the OBS software is showing that I'm still here. But for some good reason, throughout the entire stream, it's been showing that the amount of information going out has been dropping. All right, it's now a little bit past 1 o'clock, and so we're gonna pick up this discussion. So black holes have a constant density. They just. So wait, I don't want to say that. We're gonna with the math, the calculations that I've done, it assumes that black holes have constant density, but I myself don't know that. I don't know if they have constant density. But if they do have constant density, then the situation would be that black holes, of course, are bigger or smaller based off of their mass, of course. Because their Schwarzschild radius is proportional to their mass. So the bigger their mass, the bigger the radius would be, or the bigger they'd be. So no one knows the answer to that. Okay. Yeah, I'm starting to wonder if the situation is my connection or if it's something else. Well, guys, I really enjoyed the stream, and again, we're going to pick up where we left off for our next stream because I want to discuss tidal forces. Well, we could check that actually. So a black hole of the size of the universe is approximately the density. So, all right. So, what is the mass of the universe in kilograms? In fact, I think in my very first stream, we calculated the mass of the universe, the baryonic mass of the universe. I think. Oh no, with dark matter included. Actually, does anybody know the answer to that quickly? We can probably see what the density would end up coming out to be really fast. I keep going in and out. I am so sorry. But I was quickly saying that what we could do is we can determine what the mass of the universe is in units of kilograms, plug it into our program here, and see what the density comes up to be. Observable universe, right? So let's see. I'm gonna go online and look at this. So mass of universe in kilograms. Oh, wait a second. We can probably look at this from another perspective, actually. All right, I have it. So the mass of the universe is on the order of 10 to the 52 kilograms. That sounds about right, if I'm remembering the very first stream correctly. So 6E52, and so the information I'm getting, I'm going to go ahead and post it in the chat. So I just posted the link from where I'm getting the mass of the universe from. And so what I'm going to go ahead and do is use their value of 6 times 10 to the 52 kilograms. And I'm going to rerun our program with that information. So the other one's density. Let's see what happens. So given a black hole mass of 6 times 10 to the 52 kilograms, we're going to get a density of 2 times 10 to the negative 26. And according to what I'm seeing online from the same website, this calculation is about 2 orders of magnitude off. Is it 51 from that article? Is that what it says? So in the third paragraph, the second to last sentence, I was just quickly scanning, and it looks like it says factor holds. Then the total mass in the universe would be about 6 times 10 to the 52. Let's see. My mass is 10 times too big. Huh. Well, if that is the case, then that would be the correction, right? Let's see. Let's go ahead and redo it then. But in the article, it does say 6 times 10 to the 52. But let's drop it by a factor of 10, and let's see what we get. Okay, that actually went the opposite direction of what I expected. Factor of 100. By dropping it to 6 times 10 to the... I haven't really read this article. I just went online and found an article. But... And I'm going to quickly read through what they actually have here. But if I'm not mistaken, I mean, I remember doing this calculation, and maybe I shouldn't use their third paragraph estimate for the universe's total mass. Maybe I should use their estimate in the fourth paragraph. There they quote 1 times 10 to the 53 kilograms. Yeah, they changed it further down, right? That's what I'm seeing here too in the fourth paragraph. So let's use that instead. I thought I remember it being somewhere in the order of 10 to the 52 kilograms. I could look at I could look at that PDF that we generated with the very first stream. Let's go ahead and run it with that and see what happens. I'm just curious. And so this solution is actually closer to what they calculated for the density in the same document here. All right. Well, guys, I really did have a lot of fun doing this. I hope you guys had some fun as well. Yeah, so what is that? trying to think of what is that? Hubble's law, right? So as you reach the edge of the observable universe, you have things that are receding at the speed of c, right? I think that should be Hubble's law. I did not notice that. Is that when it was written? It's a while ago then. Thanks, Pyrrha. I'll do that. So wait, so by definition, the observable universe must be a black hole? Um well, the definition of a black hole is that all the mass must be encompassed within the Schwarzschild radius, right? So, but yeah, we're definitely going to continue this discussion during our next stream when we move on to talk about tidal forces. But guys, thanks for like coming and hanging out with me, talking about black holes and stuff. Wait, we see. Oh, Uncle Bill Druin, you got to point me to the paper for that. So you're saying we see objects that are moving away from us faster than c? Right. Hmm. I'm gonna think about what you're saying there. And I'll definitely ask some questions about what you're saying there after our stream. But guys, thanks for hanging out. I'll be back on next week, Wednesday, at 12 o'clock p.m. Central. Right. I was getting ready to say I understand what Larry's saying. Okay. All right. Yeah, we can continue the discussion, offline. But all right, guys. I'll see you next week. All right. Bye.